Have you ever wondered what's really going on when you mix two liquids? I mean, sometimes they blend together perfectly, and other times they just refuse. It looks simple on the surface, but it's all run by this amazing set of invisible rules. So let's dive in and pull back the curtain on the science of solutions.
Right, so think about something like alcohol and water, or as our source material mentions, methanol and ethanol. You pour them together and they just work. They become one single, totally uniform liquid. It's clean, it's predictable, but what is it on a molecular level that makes that perfect mix happen?
And then you've got the total opposite. The classic example everyone knows is oil and water, but you could also talk about castor oil and water. You can shake that bottle all day long and they will always separate back into their own layers. It's like they're molecular enemies. So what gives? What is the secret code that decides if two liquids are going to be friends or foes?
Well, to get a handle on all the messy real-world examples, we first have to understand the perfect scenario. It's what scientists call an ideal solution. Think of it as a perfect model, where everything plays by the rules exactly as you'd predict.
And this slide just lays it out so clearly. On the one hand, you have that ideal mix. 100 milliliters of methanol plus 100 milliliters of ethanol gives you exactly 200 milliliters. No surprises, no temperature change, nothing. But then, look at the real mix. You take 100 milliliters of sulfuric acid and 100 milliliters of water, and you somehow end up with only about 180 milliliters of liquid, and it gets hot. How does that even happen? Where did that volume go?
So this perfect, predictable world is governed by a rule called Raoult's law. It's all about a liquid's tendency to escape into the air as a vapor, what we call vapor pressure. Raoult's law is super simple. It just says that for any liquid in the mix, its vapor pressure is directly tied to its mole fraction, which is just a fancy way of saying how much of it is in there. The more you have of liquid A, the more A vapor you're going to get. It's beautiful, straightforward stuff.
And the formula looks just as clean as the idea itself. The vapor pressure you get from component A is just its percentage in the mix times the pressure it would have all by itself. See? Perfect, predictable math. But as we've already seen with that sulfuric acid, reality is rarely this neat and tidy. Okay, so let's leave that perfect world behind for a minute, because most solutions you'll ever encounter are, well, messy. They're what we call real or non-ideal solutions, and this is where those simple rules start to bend and break. Let's go right back to that wild sulfuric acid example. The fact that the volume actually shrinks and heat is released is a huge clue. It's telling us the molecules are interacting in ways Raoult's simple law just can't predict. They're pulling on each other, rearranging themselves into a more compact structure that takes up less space and gives off energy as heat. So what are the telltale signs of a real solution? Well, for starters, they do not follow Raoult's law. When you mix them, there's almost always a temperature change. It might get hot like the acid, or it might get cold. The final volume is almost never just a simple sum of the parts. And here's the kicker. Just about every solution you've ever interacted with, from your morning coffee to the oceans themselves, is a real solution. Now, to really wrap our heads around all of this, we need to zoom out a little. There's a bigger concept that connects everything from a simple mixture to the states of matter themselves, and that concept is the idea of a phase. A phase is really just any part of a system that is the same all the way through, both chemically and physically. So, a glass of liquid water, that's one phase. But if you drop some ice cubes in it, you now have two distinct phases. You've got a solid phase, the ice, and a liquid phase, the water. They're both H2O, but they're in different physical states. And if you look at this table, you can see the pattern. A glass of just water is one phase. Add ice, now you've got two. Mix in something that won't dissolve, like carbon tetrachloride or oil, and you've added another phase. So you can even get three phases with ice, water, and oil, all in the same container. It's all about these distinct, uniform regions. But is there a way to predict how all this works? Well, you're in luck. It turns out there is a master code. There's a single, incredibly powerful equation that lets us map out the behavior of pretty much any system you can think of. It's called Gibbs's phase rule. And honestly, it's one of the cornerstones of physical chemistry. And there it is. Looks pretty simple, right? F equals C minus P plus 2. Don't let the letters fool you. This little equation is an absolute powerhouse. It's the link between the number of chemicals, the number of phases, and what's called the freedom of a system. Let's break down what that really means. So let's crack this code. C is the number of chemical components. For water, that's just one, H2O.
P is the number of phases we just talked about, solid, liquid, gas. The really cool one is F, the degrees of freedom. The best way to think about it is as the system's wiggle room. It tells you how many variables, like temperature and pressure, you can change independently while keeping all the phases you have in perfect balance.
This rule is basically the key that unlocks something called a phase diagram. And a phase diagram is exactly what it sounds like. It's a map for a substance. But instead of showing roads and cities, it shows you which phase, solid, liquid, or gas, is going to be stable at any given temperature and pressure.
So, picture this map for water. In one area, at cold temperatures, you find ice. In another, you get liquid. At high temperatures, you get steam. The lines between these areas are where two phases can exist together. But look closer. What about that one single, incredible point where all three borders meet? That's called the triple point. And our phase rule can tell us exactly what's so special about it.
Let's just plug in the numbers. It's easy. We have one component, C, which is just water. And at this special point, we have three phases P, solid, liquid, and gas. So our equation becomes F equals 1 minus 3 plus 2. And what does that equal? 0.
0 degrees of freedom. Now that is profound. It means there is only one single exact temperature, 0.01 degrees Celsius, and one single exact pressure where solid ice, liquid water, and water vapor can all exist together in perfect balance. If you nudge the temperature or pressure even a tiny bit, one of those phases will vanish. The system is totally locked in place. It's a fundamental constant of the universe for water.
So, okay, we've talked about ideal solutions and phase rules and triple points, but why does any of this matter? Well, it turns out these abstract ideas have huge real-world consequences, especially in fields like medicine and all kinds of industry.
This is not just theory for a textbook. Think about making a new medicine. It has to be a stable solution so it can be delivered safely and effectively. Pharmacists use these exact principles and phase rules to figure out the precise conditions needed to create a drug that won't separate on the shelf, or worse, inside your body. From creating life-saving drugs to industrial processes like distillation, these rules are the invisible blueprint for so much of our modern world.
When you think about it, the laws of solutions and phases are just a perfect example of these hidden scientific principles that are running everything behind the scenes, from the drink in your cup to the fuel in your car. It really makes you wonder, what other invisible rules are out there, quietly shaping our world, just waiting for us to discover them?